But each of these things here, this here is non-negative. This here is non-negative. And you see the sum of these two numbers is bounded by epsilon. So it means that each of them must be at most epsilon, right? Yeah.
Are you able to explain again what you did to break up P star into the intersection of A to C?
Okay. So I have here the interval. I have here the interval from A to B. Here I have C. And the star partition is the one that has all of the dividing points of the original partition, P, and then also C. So the partition looks like this. Maybe this here would be the partition. And now I'm thinking about, so the sum here, in the sum from the star partition, it would look like this. And I'm summing over all I, right? But I can look at where I'm summing over just those intervals up to here. Right? I can look at where I'm just summing over these intervals, and then I can look at where I'm summing over those intervals, right? And so that's what I mean. So this here is now where you're summing over all the I, but you can also just summing over the I's that are less or equal to C, and the I's that are, in this range. Right? Okay, so that's okay. So this here proves this here. So what this proves is that if you take this function and is integrable on this interval, and you now restrict it to either of those, they are also integrable. Right? That's what it actually proves. But it's easy to see that it also, with a little bit, maybe I'll leave this for you, but that through the proof, we also get that this sum here will have to be equal to the sum of these two. Right? But really what I, technically speaking, proved was just this part here. Okay. But again, all of the details for this are in the notes. Okay. Now the next thing I want to, okay, so yeah, so I will let's talk about one corollary of this. So it's the corollary really not of this fourth property, but on the third property. So the third property was this with so the third property was this property here, over here. So I want to talk about a corollary of this one here. So now I have a function. I'm assuming both the function and the function that is the absolute value. So the function that is absolute value means that at each point, instead of looking at f of x, I'm looking at the absolute value of f of x. This is the function. So I'm assuming that both of these functions are Riemann integrable on this interval from a to b. And then the claim is that the integral here of f is less or equal, dx, sorry, is less or equal to the integral from a. This is very simple inequality, but extremely useful. So this is the claim, right? So I'm already assuming that everything is Riemann integrable, so I don't need to prove anything like that. I just need to establish this inequality. And so to do that, I'm just looking at f. Well, f is less or equal to the absolute value. If f is positive, it's equal to the absolute value. If it's negative, this here is non-negative anyway. So this is clear. This is clearly for all x. But it's also clear that if I take minus f, you see, this is also less than this, right? But now taken together, so those two things, so now the first one, so let's say star here and double star here. So star here plus property 3 from over there, this just gives us that the integral of f from a to b dx is less or equal to the integral of the absolute value. Right, this is from star and 3. But if we take double star here, plus 3, well, then we have that, right, so this here, so we have that the integral of minus f dx is less or equal to the integral, like this. Right? But this one here is, you can just think about this here as minus 1. This is like minus 1 times this function, right? So minus 1 just comes out. That was like number 1. So this here is like minus 1 times the integral from a to b of f dx. But this is, of course, the same as minus the integral from a to b f dx, right? So you see that, so this here, so the second here implies that minus the integral from a to b f dx is less or equal to this thing here, right? And so now you have this thing here and that thing here, and so together it just means that the absolute value of this is bounded by this, right? And so that's really this corollary. Okay. The next thing I want to talk about, so this is how to evaluate integrals, right? And so there you have this, the fundamental theorem of calculus. And so we'll give two versions of that. So how to evaluate integrals. And so this is the fundamental theorem of calculus. Okay, and now what does the fundamental theorem of calculus? So let's give version 1. So version 1. Version 1 is that if you take a function f, and f here is continuous, and you're looking at the integral, you're looking at, so you have a function. I don't really think about it as two versions. But the version, but I divided it into two versions here. So the function, if f is continuous, say on the interval on this interval here, and you define a function f of x, which is the integral from a to x of f of s ds. Right, you see, for each fixed x in the interval here, well, if you're thinking about the function little f, if little f was continuous on the whole interval, so it's continuous on, right, so f here is continuous on the interval from a to x, right, so it's when you restrict it, it's still continuous. So this means that it's integrable, right, and so this here gives you a number, right. And so for each x, you can think about this number here. So this gives you a function capital F, right? And the claim is that this function here, So the claim is that the function capital F defined this way is differentiable. So capital F is differentiable. And the derivative of this at x is little f of x. And maybe I'll just, yeah, so that's the claim. Okay, let's try to prove that. So let's try to prove. So we want to prove that this function, so we want to prove, want to show that f prime exists, right? At x0, right? If you want to prove that it exists, then you need to look at the difference quotient. So we need to look at this difference quotient. And we need to prove that this thing here has a limit as x go to x0, right? So x0 is fixed, and you want to prove that it has a limit, right? Let's, so in order to estimate this, let me not divide first. Let me just look at what this difference here is, right? And then afterwards, I'm going to divide by x minus x0. So if I'm looking at this, let's, for the sake of argument, assume that x is bigger than x0. Of course, I need to also see when I'm approaching x0 from the other side, right? But the argument for that is similar. So I just assume that x is bigger than x0. Well, this difference here, well, the function, so this function here, so let me just write it over here so I have a little more space. So this difference here, well, the function, this here is the integral from a to x f of s ds. And this thing here is the integral from a to x0 f of s ds, right? But this first integral here, I can use this fourth rule that I maybe don't have anymore, but the fourth rule is saying that you can split it up, an integral, you can split it up. So here if you have a, then you have x0, and then you have x. If you want to integrate little f over this, it's the same as integrating over this plus the integral over that, right? So I do that. So this one here, I break into two pieces. I integrate from a to x0, f of s ds, and then I take the second piece, which is from x0 to x, and then minus the integral from a to x0 of f of s ds. Okay? But now you see that this one here cancel out with that, right? And so this difference is just the integral from x0 to x f of s ds. Okay. So what we have is we have that this difference here, f of x minus f of x0. We know that this difference here is equal to this integral here. Now, let me use this to bound this thing here from above and bound it from below. You see, this integral here, this function here, So this function here, if you're looking at this integral here, sorry, from f of s ds, well, this function here is smaller than the max, right? The function is continuous, so max and sup is the same. The max or sup, whatever you want, on that interval, right? So this thing here is less than the integral of, if you will, x0 to x of the sup of f on this interval here. Right, but this is just a constant, right? And so this here is just, this is just like the sup of the function on this little interval times, right? So this is a constant, so this just pops out, and then it's just the integral of 1 on this, but that's just the length of the interval. So it's this here times the length of the interval, and the length of the interval is this, right? So this thing here is less than that, right? Likewise, this function here on this little interval is bigger or equal to the inf. So this is bigger than, right, than if you were just integrating the inf of the function on this same interval. But the inf, this is just a constant. This pops out. So this thing here is just the inf of the function on this interval here times the length of the interval. Okay, like that. Okay, so now I can, and remember that this thing here was equal to the difference, right? So now I can just record this. So what I have is now, what I'm interested in is in the difference in capital F. So what I'm interested in is, of course, I really want to look at the difference quotient, but I can do this in just a second. So I'm interested in the difference of the function at those 2 points, right? I know that that difference is equal to that integral here, and that integral is bounded from above by this and below by that. So I can now just write that this difference here, maybe I should write it so I have a little more space, somehow f of x minus f of x0, the difference is bounded from above by this thing here, the sup of f on this little interval times x minus x0, and it's bounded from below by the inf on that same interval times the length of the interval, right? So now we can go to the difference quotient because we just divide by x minus x0 on both sides. X is bigger than x0. So you have this thing here. So you have this difference quotient here. And that's what we want to show has a limit. And now we have that this is less than sup of f on this little interval here. And it's bigger or equal to the inf of f on that same little interval. Right? But you see that as x here, but now you have that as x goes to x0, right? So now as x goes to x0, right, the values, not just the value at x, but actually in this whole interval here, the values goes to what the values is at x0, right? So you see that this here, the right-hand side here goes to f of x, little f of x0, and the left-hand side go to little of f of x0, right? So this means that this thing is squeezed between these two numbers that goes to the same number. So this difference quotient also goes. So this difference quotient here goes to f of x0, right? Because it's squeezed between those two numbers that converge to the same number, namely to f of x, little f of x0. Right? So this here proves that it's, but technically speaking, I only did it where I'm assuming that x was bigger than x0. If you let, so you also need to check when x is strictly less than x0 and it's converging to x0 from below. But with trivial modification, the same proof works. And so, and that's done out in the notes, so I will not go through that. Okay, now let's talk about, so there's a second version of the fundamental theorem of calculus. Right, and so, I mean, again, you know, you wouldn't really eventually kind of think about it as probably as two different versions, but they're sort of slightly, you know, it's two things about the same stuff. But the second version here, so I divided it into these two versions. So the second version, so again, fundamental theorem of calculus. Version 2. And so this is the following, that you take a function f that is defined, you know, and f is defined on some interval from a to b into r, and f is differentiable. So this here exists. It's differentiable at each point. And f here, this little f, is Riemann integrable. And then the claim is that that f of b minus capital F at a is the integral from a to b of little f of x dx. Okay, so that's a claim. Right. All right. I wonder if I should just skip that. I did that. I did the proof for this out in the notes also. So maybe I'll just skip that. And then, okay, so now, but let me look at an example where I'm applying it. And so I have, I'm looking at, so suppose I want to compute x squared from 0 to 1 dx. Suppose I want to compute that. And so in this case, I could look at, so if I sort of want to apply that version, I could think about, suppose I'm looking at f of x equal to x to the power 3 over 3. Right? Suppose I'm looking at this. Well, if I'm looking at this function, I know that capital F of x is equal to the derivative of this is just x squared, right? So this, say, an x squared is now, of course, it's continuous, so it's integrable, right? So this means that by this second version, of the fundamental theorem of calculus, then we have that that f of 1 minus f of 0 is equal to the integral, right, of the derivative, because the derivative is integrable, so 0 to 1 of x squared dx, right? But this here is now just evaluating this function here. So this here is 1/3 minus 0. So this original integral is 1/3, right? Okay, so the next thing, right? So the next thing I want to talk about is improper integrals. Okay. So this here concludes. This here was stuff I actually had from the previous lecture. That was why I skipped a couple of things, but the details for the things I skipped is in the notes, and the things I skipped is very similar to things I went through here anyway. Okay, so now let me look at improper integrals. And there is a couple of versions of this. So we will look at two versions of this. One is where the interval is, so we will look at improper integrals. So I'm going to look at two versions, so two versions. Version 1 is where the integral is unbounded. The interval is unbounded. And the second version is where the function is unbounded. Okay. Now, in the first version, then you take looking at a function f, and this function is integrable. So f here is integrable from a to b for all. So a here is fixed, but it's integrable for all b bigger than a. So a is fixed, so a here fixed, and it's integrable like that. Okay. Then what we are interested in, so again, if you're thinking about the integral as a kind of, think about the integral as the weighted area. So, and weight just means that if the function is negative in a stretch, then the area there will count with a minus sign, right? So this here is, so what we're interested in is we're interested in making sense of the area, the weighted area below the graph, where we go all the way out to infinity, okay? And so this is, does this make sense? So this is in this case the improper integral. It's improper because it's not a bounded interval, right? And so yes, if this limit here of a to b, if this limit here of f of x dx, if this limit here as b goes to infinity exists, then we say that the improper integral here from a to infinity of f of x, we say that this here exists and is equal to this limit. Okay? So this is one version of the improper integrals, and the other version is of the improper integral is the following. So the second version, so this is where f here is unbounded. In a minute, I'll look at examples of both things. So the function is unbounded, so it's defined on, but f here is supposed to be integrable on, say, a to b. Right, sorry, it's supposed to be integral from, c to b for all c bigger than, so c here, c is bigger than some a and less than b. So think here about, here you have a, here you have b. So a and b in this case are fixed, but the function is not bounded. It's not maybe even defined at a, right? It's not really defined at a, but it is. But it is integrable on, if you go anywhere strictly to the right of a, then it is integrable on this interval here. And so if this limit, so if this limit here, as c goes to a, the integral from c to b of f of x dx, if this limit here exists, then we say that this improper integral from c to b, sorry, a to b of f of x dx, this is an improper integral because the function is not bounded on this whole integral. It's not even defined at a. If this here, we say that this thing here is equal to this limit as c goes to a of c b f of x dx. Okay. And so, the improper integral actually often appear in things. Okay, so let me look at examples of this. So I will look at example of this, and I will look, so again, there's these two versions where the interval is unbounded or the function is unbounded, right? Of course, there's all kind of variation of this, right? Here I looked at where the function was unbounded to the left, but you could do the same to the right. It could be this interval here, this interval where the interval was unbounded. When I explained what it means, I did it as if the interval was unbounded to the right. But of course, you could also look at unbounded to the left, or you could even look at where it was unbounded both to the right and to the left. Okay. But let me look at some examples. And so the first example, again, the first two examples will be where the interval is unbounded. So the first example here is where the interval is unbounded, and we're looking at the interval is 1 to infinity, and we're looking at the function f of x equal to 1 over x squared. Right? And I'm interested in, and the question is, does the improper integral, this here, of 1 over x squared dx, does this exist? That's the question. Right? And so we use the fundamental theorem of calculus to determine that. We observe that if we're looking at f of x, which is 1 over x, then the derivative here is of this function here, this is 1 over x squared. Okay? So this is what we observe. So therefore, it means that if you integrating from 1 to b of 1 over x squared dx, this thing here is the same as f of b minus f of 1, right? And so using this, and we know what f is, you have that this is minus 1 over b, and it's minus 1 over b. This is what you get from this. And here you're getting 1 plus 1, like this, right? And so you see that this thing here, as b goes to infinity, this here converts to 0. So this here converts to 1. So indeed, this improper, yes, is the answer, and what it is equal to, right? Because it converts to 1, it's equal to 1. Okay? So again, if you're thinking about it, it's sort of a little bit like what we did for series, that you're summing infinitely many numbers. So here you're looking at something, and you're looking at the area, but the area actually is finite, even though it continues on forever. So that's one version of it. Suppose that instead of 1 over x squared, so 1 over the property that the function 1 over x squared has is that it goes really quite fast to 0. As x goes to infinity, 1 over x squared goes really pretty fast to 0. Suppose I look at a function that does go to 0. Right? If it doesn't go to 0, right? If the function doesn't go to 0, right? If it was kind of, let's say that it was staying above a certain line, well, then the area below the graph would, of course, be larger than this thing, and that would be infinite, so it's not going to converge, right? So it will have to kind of go to 0 in some way. So example 2, I'm looking at another function, still goes to 0. Again, the interval is the same from 1 to infinity, and the function is now, this time, it's 1 over x. It still goes to 0, so maybe it has a chance. Let's see. If you now take the integral from 1 to x of 1 to b, sorry, of 1 over x dx, well, again, you use the fundamental theorem of calculus. If you're looking at the function f of x equal to log of x, the derivative of log is 1 over x. Right? So this thing here, by the fundamental theorem of calculus, this second version of fundamental theorem of calculus, is f of b minus f of 1. And that is log of b minus log of 1. Log of 1 is 0, so this is just log of b. But as b goes to infinity, this here actually goes, it's not bounded, it tends to wander off to infinity, right? So this improper integral here, this one here, does not exist. Right? It actually, it's like the area below this function here would actually be like infinite. Right? It does not go to 0 fast enough. Okay. So that's examples of where the interval is unbounded. Suppose that we look at examples where instead of the interval is being unbounded, the function is unbounded. So let's look at some example of that. Suppose you take, so now, suppose you take the interval from, so the interval is bounded, but the function is not unbounded. the interval is bounded, but the function is unbounded. So I'm looking at first f of x equal to 1 over square root of x. As x goes to 0, square root of 0, x goes to 0. So this means that 1 over it goes to infinity. So this function is not bounded. But if I'm now looking at, so I want to look at the improper integral, where I'm taking this function. The function is blowing up as I'm going close to 0, right? Blowing up like that. And I want to see, does this here, does this improper integral here, does this exist? Right, that's a question. And so in order to figure that out, I use the fundamental theorem of calculus again. So if I take the function, f of x equal to 2 times square root of x, and I now take the derivative of this, then I get 1 over square root of x. Okay. And so this means that if you now look at so this means that if you're now looking at the integral here of by this integral from a, say, to 1 of 1 over square root of x, a here is strictly positive, dx. This thing here is capital F of 1 minus capital F of a. And so capital F was this function here. So this is 2, right? 2 square root of 1, that's 1. So it's 2 minus 2 square root of a. But now as a goes to 0, this here converts to 2. Right? So this improper integral exists. So yes, this one here exists. And is equal to 2. Okay. Let's look at one last example of this. And so this is another example where the function is, so again, you know, in this sort of example, the function was unbounded, it's blowing up, it's going to infinity, but the area below the graph, that's what we calculated, is still actually finite, right? But what if the function is blowing up faster than this, right? So this is an example like this, that if you take this, it's again the interval from 0 to 1, and the function is now it's going to infinite faster as x goes to 0. So this is the function. And so now we again asking is, does the improper integral, so does this improper integral here exist? And let's see if it exists or not. So we use the fundamental theorem of calculus again. We observe that the function f of x equal to log of x, that the derivative of this function is just 1 over x. So this means that if we integrate from a is now again strictly positive. Strictly positive. So if we're looking at this integral here, this here is because of the second version of the fundamental theorem of calculus. We have that this here is f in 1 minus f in a. And this thing is now log of 1, that's 0, minus log of a. Log of a is, right, so log of a, so this is like that. And now remember that log, the log function here, the log function looks like this. Right, this is the log function. So you see that as you go towards 0 here, this number here goes to minus infinity, so this here goes to infinity, right? So it doesn't converge, right? So the answer is no. Okay. And so the very last thing I want to talk about is I'll just give you a definition. So this is arc length. So suppose you take a curve in the plane. So suppose that I have a curve in the plane. So gamma of t, this is a curve, so it has in the plane, so it means that it has two coordinates called gamma of s. So I think that's what I did in the notes. So this here is the curve, and I'm assuming that f and g are differentiable, and the derivative here are continuous. So suppose I have such a curve, and S here is running in an interval from A to B. Then the length of the curve is, by definition, the integral from A to B of square root of f prime of S squared plus g prime of s squared ds. So this is the length of the curve. Maybe I'll talk a little bit more about that next time. Okay, so I'll stop here. And I'll post the notes. Any questions? Okay.